Okay, first, thanks for the invitation and thanks for everyone for attending this talk. The title, as you can see, is toward a unified model of cognitive functions. So if we are talking about to build a general purpose AI or a cognitive system, whatever you call it, I think there's three possibilities. One is what I call hybrid. The basic idea is just to use the available technology which have been developed for many years for the AI community for each of the cognitive function. Maybe we can put them together to get a system which can do almost everything. Then the second approach is what I call integrated. That approach basically say now you cannot just put the existing technology together. You need to start with some kind of overall design. Let's call it a cognitive architecture. Then you can put in different technology as different modules for different functions to make them work together. I assume most people in this audience are very familiar with this approach. Finally, there is a third possibility, which I call the unified approach. The basic idea is just basically use one technique, try to get everything. Here, the justification is what we call a different function, maybe is a different projection or perspective of the same underlying mechanism. The last one currently is only believed by a small minority, I guess. Even among the people who believe this can be done, they probably are thinking about the deep neural network. But what I'm going to talk about is a different technology, but it's roughly in the last category. By the way, clearly all these three schools of thought, now it's way too early to tell which one is the best, and each of them has its advantage and disadvantage. Today, we don't have the time to do a survey. So I will just focus on what I have been doing myself, which belong to the last category. The technique I've been using is reasoning system, which of course is not a new idea at all, right? This is actually one of the oldest ideas in AI. So very roughly speaking is the system will follow some kind of logic. And you implement that logic in a computer system and use it to solve problems. Clear strength is this is domain dependent because the logic is supposed to be general purpose. And also a logic allow you to combine different steps or rules in a flexible way. But at the same time, the weakness is well known. Many people even claim this is nothing but the symbolic AI which has died, especially when we are talking about general purpose system. I'm very familiar with all the criticism to the traditional symbolic AI, which I'm not going to explain or analyze one by one. Just basically, my answer is what I'm doing is very different. It's still in the framework of a reasoning system, but I've been working on a system named NARS for non-axiomatic reasoning system. Here, the key difference from the traditional reasoning system is it's not about theorem proving. It's not from truth to truth. But is going back to logic or reasoning in the original sense. That is about everyday thinking. I'm looking for the patterns we usually follow in normal thinking, where you'll see that's where the name non-axiomatic come from. There is no absolute truth. Okay, every belief or knowledge, whatever you call it in the system, can be wrong. Maybe modified by future experience or something like that. So this system is fully based on my own working definition of intelligence. To me, intelligence is the ability to adapt to the environment under the restriction of insufficient knowledge and resources. And this definition itself, of course, needs justification, but I have read several plays about that, so I'm not going to repeat that philosophical discussion. I just say this is my foundation of all the following discussions. That's my understanding about intelligence. So clearly today, I'm going to make a very big claim, basically saying that in this system, I can do almost everything. Given the complexity of the topic, clearly, we don't have the time to explain each of the functions that carried out in NARS. So instead, I will just focus on the big picture and focus on how those functions can be unified into the same foundation without talking about all the details. But I have publications and we have implementations of the system, which you can check later, and we can also discuss after the meeting about those kind of details. So the overall architecture of NARS is actually quite simple. It's a reasoning system. You'll see that it communicates with the outside world through a bunch of channels, some of them using the system's native language, called NARSIS. That's a formal language we developed for communication and knowledge representation. And it also can communicate with other human or computer using human language or computer language under some restriction. And also, it can directly interact with the outside world if this is implemented in a robot using sensors and actuators and so on. So all those interactions, the input part will be put together to form the system's overall experience. And some of them, the selected part, of course, will be entered into the system's memory for long-term processing. And then it's a reasoning system. It works in some kind of working cycle. In each cycle, some knowledge is selected from the memory and feed into the inference engine, which will produce some results, which will go back to become part of the system's internal experience, will become being processed further, just like the external experience. And some of them will also go directly to the outside, to the users and to the environment. So it's, in terms of architecture, there is nothing too special. The memory is a huge network, but it's not a neural network. It's what I call a concept network. And also, this is not a new idea. It's similar to, say, semantic network, knowledge graph, ontology, whatever you call it, in the big picture. So you can think it as some kind of graph where each node is a concept, and each link is a conceptual relation. But what makes this one different is the concepts can be a lot of different things. Each concept is named by a term. A term which is basically an ID. And some of the terms may correspond to words or phrase or even sentence in human language. Some of them may correspond to some, say, sensation, perception, or action when you have sensory motor channels connected. Some of them actually means nothing to the outside. It's a pure internal ID, identifier. And finally, there can be compound term, which is a structure recursively built from other terms. Very roughly speaking, that's what the memory looks like. So this is what we call a concept-centered representation. So first, again, a term names a concept. A term is nothing but an internal ID. A concept corresponds to certain elements or patterns in the system's experience. And a term, as I just mentioned, can correspond to many different things. And the relations, the basic relations are built in, but we can use them to represent many other conceptual relations. And they basically represent how one term can be used as the other, or their relationship, which I will say a little bit more later. So some minimum technical representation, okay, or discussion. So a term is ID. The simplest form of statement is two terms related by a coupler. Here, actually, it does not look like a predicate couplers. It looks more like Aristotle's term logic for some reason you will see in the following. The relation, there are several built-in relations. The simplest one is what I call inheritance, which intuitively correspond to specialization or generalization. So you can write it in this way. This is a concrete example, say like water is a type of liquid. So there is inheritance relation from water to liquid. There is a direction clearly in this relationship. Then based on that, I define the extension and intention of a given term. So in terms of graph theory, you can say that extension are the things that have a link to it. Intention are the things that have a link from it. Okay, but according to the previous interpretation of the relationship, extension of a concept are the more special ones of it, or it's a specialization. Intention include all of its generalization, roughly speaking. And we can also use this to define accurately what inheritance means in this system, which are also formally defined in my academic publications, my books, and my articles. So I'll just, here we just use them intuitively. Then based on that, I can begin to define evidence. What is evidence for a given statement? Okay. So again, here, evidence is fully specified in terms of extension and intention I just defined. Intuitively speaking, if I want to know evidence for this inheritance relation from S to P, okay, if I find something which is both instance of S and P, it's a positive evidence. The same thing for their common intention. If I find a property of P or a generalization of P, which is also a generalization of S, that counts as positive evidence. On the other hand, if there is something which is in S but not in P, that's negative evidence. Also on the intention side, if there is a property of P but not a property of S, that's negative evidence. Later we will see concrete example, and also this definition, of course, is in a highly idealized situation, which will be extended later to normal situation where later you will see everything is true to a degree, as I already claimed before. Okay, but in this definition, we only talk about idealized case. And now you'll see we can simply count the amount of positive and negative evidence and add them together as the total evidence. Okay, again, that we can just take this intuitively, say that I'm testing this relationship multiple times. And so each testing will give me some evidence. And some testing means indicate that this relation is true or is successful in the current situation. So that's positive evidence. Otherwise, it's negative. And then I summarize this into a pair of numbers. This is probably the first notable technical difference between NARS with everything else out there. That is how to handle truth value. To take truth is a matter of degree. Again, it's quite common now. but it's uncommon. What is uncommon here is not only I'm using a number, I'm actually using two numbers. The first number is called frequency. This is easy to understand. This is the amount of positive evidence among all evidence. That is, I tried it 100 times, 80% of the time it's true, so that, it's 0.8. It's kind of like probability, but it's not probability. You see that in probability, you should take the limit of this relative frequency if you take the frequencies interpretation of probability theory. But in NARS, it's completely based on available evidence. So it does not take the limit. And also you can see that as a system collecting more evidence, this number will be modified for sure, because both numbers may change, this positive and total amount of evidence. The second one is unique in NARS. It's not like anything else in other system. It's what I call confidence. This word has been used in many systems, but this way to define is unique. You see, according to what I said, confidence is a ratio, also is something between 0 and 1. It compares what you already know with what you already know plus 1. What's that supposed to mean? This plus 1 actually can be replaced by another positive constant. It's basically you compare what you already know with future evidence. But the future can be infinite. Well, here we all compare with the same amount of future evidence. So here is basically saying that compared to the next piece of information or evidence, how much you already know. So this is, how much you will know after you get the next piece. So if you know nothing, this W equal to 0, right? If you test this once, then this will be 1 out of 2. If you test this relation twice, there will be 2 out of 3, 3 out of 4, and so on. You'll see that this one will increase when you get more and more evidence, which basically indicate how stable or reliable your frequency value is. But this confidence will never reach 1. As you can see from the formula, it will convert to 1 when you get more evidence. So this is actually the technical sense of what I call non-axiomatic, meaning that everyone is confident to a certain degree. It can be high, it can be relatively low, but no matter what, it can be modified in the future. So first, with this representation, it looks pretty simple, but if you interpret it in different contexts, actually it can represent several different types of uncertainty. Not only randomness is covered by probability theory or anything based on probability theory. It can also capture the idea behind the fuzzy logic. And also it can be used to represent systems ignorance and vagueness and inconsistency and so on. And for each of them, I have publications, so I'm not going to go into detail again because of the time restriction. And also, my work is strongly influenced by a lot of work in psychology. For example, this concept model I just mentioned, the meaning of a concept in NARS consists of its extension and intention, or in other words, what a concept means based on at the current time, what instance or property the system knows about this concept. Okay. So this opinion also can be used to unify several theory of concepts in psychology, like prototype theory, exemplar theory, and theory theory, and so on. Okay. And all of them become a special case of my conceptual model. Again, no time for detail. One important point I want to stress very strongly is the relationship or difference between NARS and the traditional symbolic AI. Okay. Most people, if they only spend 5 or 10 minutes to browse my design or NARS or take a demo, they will say, "Oh, this is symbolic AI again," but it is not. Clearly, there are a lot of similarity between NARS and symbolic AI. The key difference, if I have to mention one, I already mentioned this is not self-improving, right? But also symbolic AI are not completely about self-improving. But there is one thing which is even more fundamental, that is about meaning, okay? How can a symbol get its meaning in symbolic AI and in the so-called computationalism in cognitive science is basically shown in this picture. That is, symbol, as the name suggests, symbolizes something outside the system. Okay, so you may have objects, you may have object relationship among objects, and then you build an interpretation or a denotation. You say that a string in the system's mind represents or refers to or denotes or symbolizes something in the outside world, is shown in this very simple diagram. Okay, there are floors, there is a pot, and the floor is in the pot. That's part of the reality. Okay, you represent that relationship in your mind with words and the relationship among words. And this is this interpretation which link your concept to outside object, which gave this concept its meaning. Okay, what floor means? Well, that's what it refers to, outside the world. That is the one basic assumption behind the so-called symbolic AI. That's what symbol means. Okay, in almost all symbolic AI systems to different degrees. But I have already mentioned this. That's not what a concept means in NARS. It is not a symbol. If you have to say, because it's a string of characters, it have to be a symbol. Well, you can say it that way, but even in that sense, it is not a symbol of an object. It's a symbol of part of the system's experience. Okay, this is a key difference. This is a key difference, and concepts is basically an internal construction. It's of course not arbitrary. It's based on experience in a general sense, or you can say it's based on the system's interaction with its outside world. Okay, but it's not a label or a name of an object. And also that means that you cannot compare your concept system with the reality to decide what is right and what is wrong. There is no such a thing. The only thing you can use is your experience. Okay. And of course, you don't use your experience as a whole. You cut it into pieces, you generalize it, you process it, and so on to get your concepts. But that's what you have. Okay. So to summarize what I call experience grounded semantics in NARS, a concept is the internal data structure. Okay. It has a name. It's called a term, which the meaning is decided by its role in the system's experience, especially by its extension and intention. And also a statement corresponds to experience conceptual relation as implied by my previous definition of truth value. Okay. You see, again, a term does not symbolize any external objects. So one result you can see, there is no symbol grounding problem. Okay, by definition, all the concepts are already grounded in the system's experience because that's where it comes from. And a meaning of a concept clearly depends on the system's body, meaning that sensory sensors and actuators, the current situation, and also a change according to the change of the experience. All of them are already implied by this definition. And the truth value of a statement, this is also a key difference. Okay. Traditionally, when we talk about truth value, we compare a statement with the reality. If it correctly represents the reality, it's true, otherwise it's false. Here, my assumption is you don't really have direct access to the reality, okay? What you can have is your experience. So what you do is you compare a statement with your experience, including other statements you get from outside. And you decide to what degree they agree with each other. That is your truth value. Okay? So this is very different from the conventional usage of the term. I have to stress very strong. And the representation itself is very powerful, as I see that I have already shown that what I call a term is an internal ID, which can be used to indicate a lot of different things. In the simplest case, it's just a sequence of characters used as an ID, but it can be a compound, it can have internal structures, it can correspond to a signal reported by a sensor or some pattern formed from those things. And the statement itself, well, clearly you can give a sentence a name, right? So a statement itself is a compound term. It's just a term with a truth value, which indicate, how it's compared with the experience. And the event is a special statement where the truth value actually have a timestamp associated. Say, I'm not talking about something which is always the case. I'm talking about, the current moment or a moment a few minutes before or something like that. And also, we can use this to represent the operations the system can execute, which is also a term. It's just this term corresponds to an action the system can carry out. And similarly, for a goal to be achieved. And this part is quite similar. I get the inspiration from logic programming, just like in Prolog, right? It just now in NARS, everything become a matter of degree. Okay? So you'll see that in this way, this language uniformly represents what we call definitional, declarative, episodic, procedure knowledge. But to still keep their difference. You can still say that this is different from another, but they all share or they're all covered using the same formal language under my interpretation. So let's see a little bit of details. There is a large number of inference rules. Clearly, we don't have the time to go through all of them. So I will just talk about the most fundamental rules. Like, for example, the deduction rule. Okay. First, you'll see this is the formal definition. We have two inheritance relation where the subject of one is the same as the predicate of the other. So this forms a kind of like inheritance chain, right? This, because this inheritance relation is clearly transitive, so we can say, if M is a type of P, S is the type of M, then S is a type of P. Okay, this is, implemented in almost every reasoning system in different form. What makes NARS different, of course, because it's multi-valued. You need to calculate the truth value of the conclusion according to the truth value of the premise, plus, this is deduction. And here I have a bunch of truth value functions in NARS to handle this calculation. Again, no time for the detail, but the basic idea is, first, this is not probability calculation. Okay, frequency is similar to probability, but confidence is not even a probability value in the first place. Okay. So this cannot be based on probability calculation, even though there's some overlap, and sometimes you will see the same result or similar results from my system and probability-based system. But they're not exactly the same. This is not derived from probability. Instead, you'll see that technically, I treat all the measurements in my system as an extension of Boolean value. Okay, a Boolean variable, take 0 and 1. My measurements, as I define, you see that frequency, confidence, and many others take a real number in between. Okay, so that I also extended the Boolean operators and or and not from binary to a real number between 0 and 1. The formula itself is quite simple, but there is a justification in my publication, which I'm going to skip. Okay, so here we just take it as they are. So this is the function we use. And by the way, this AND operation in the system actually is nothing but a multiplication of the numbers. Okay, you can see from the following calculation. So this is a graphical representation. So this is kind of like if you have two inheritance link, connected head to tail, and then you can combine them into one direct link, something like that. And this is a concrete example. If the system believes bird is a type of animal and robin is a type of bird, you'll see here I'm just using the default truth value for positive statement or affirmative statement, where frequency is 1 means 100% positive. Confidence, well, I would just use the same constant, just say that they're supported by the same amount of evidence to make things simple. Okay. Then you will see that the conclusion is also affirmative. The confidence level is a little bit lower than the premise because it's kind of like indirectly supported, intuitively speaking. Okay. There is nothing special about this one, so I'm going to go through it quickly. And this is probably the most representative inference rule in NARS, induction. Okay, you'll see the format is also syllogistic, meaning that two premise share one common term. Here, the difference is the shared term is a common subject. Okay, let's directly see an example in this case. If you know swan is a type of bird, if you know swan can swim, can you say bird can swim? Well, this is, if I put it in this way, this is a typical fallacy of overgeneralization in every logic. Okay, this is why induction is difficult, because everyone is doing this, but it cannot be justified. The conclusion can be wrong. It's usually wrong. Very often it's wrong. Okay, but how can this be justified in NARS? It's completely because of the truth value and the semantics behind the truth value. Okay, so in NARS, the conclusion does not make a claim about birds in the world. It's basically saying that as far as I know, I have evidence for birds to be swimmers. And the evidence is provided in this case by swan. Okay, here in each inference, I'm basically assume this premise contains everything I need to think about at this moment. And from that piece of knowledge, what I can say. Well, I can say bird can swim, but you see the confidence level is much lower than that of deduction with the same default truth value in the premise. Okay, that is why induction, in this case, is from one single piece of evidence. It cannot be very strong. Usually we just call it a hypothesis. Okay? Even though in NARS, maybe you have already guessed what we call hypothesis, what we call belief, what we call fact, or knowledge. The difference is a matter of degree. Okay, so beliefs with low confidence level, yeah, that's a hypothesis. Semantically, it can also handle abduction. Here, the common term is the predicate. By the way, this is the elegance of why I use term logic or syllogistic logic rather than predicate calculus. Okay. Because in term logic, different type of reasoning, especially induction, abduction, and deduction can be very elegantly combined into the same pattern. This is discovered by C.S. Peirce many years ago. Okay. So here, let's again see an example. If we know that seabirds in general can swim, and I know a gull can swim, Does that tell me that Gao is a type of seabird? Of course, it is not enough, but it gives me evidence to believe that, okay, to a certain degree. So what if I'm collecting evidence from different sources than they give me different truth value? Well, that's where revision begins to become necessary, so that well, you can see this is basically a weighted average or something like that. Okay, so you pull your evidence from different sources together to get what? To get a more confident conclusion. Okay, so the result in this example, if you check where the number come from, actually it's also very simple, similar to statistics. This conclusion basically say that 2/3 of the bird I know are swim. Okay, but different from typical statistics. Here, everything is done by inference rules, and also it's not like, collect all the information or data together and run an algorithm over them. No, it's taking evidence piece by piece. And each piece may revise some of the existing belief in an incremental, cumulative manner. So again, a big claim, this logic, which I call non-axiomatic logic, with a whole bunch of other rules, of course, not just the four I mentioned, actually share the intuition with many so-called non-classical logic as in this list, okay, here or there, but it's also different from them here or there, each of them. And also it explains a whole bunch of things that discovered in psychology or in logic. Again, for each of them, I already have publications if you're interested. We are not going into details. But the most interesting thing, again, I'm going to stress, is I'm not having a lot of parts, each of them solve one of those problems that I put them together. NARS is one logic. It does all of them. Okay? Of course, with multiple inference rules in it, but they're all justified according to the same semantic foundation. That's what I call a unified solution to the problems. So a quick example. So you'll see that if I know Tweety is robin, robin is a type of bird, bird is a type of animal. By the way, Tweety is put in curly braces because it's a proper name, which is handled differently. And the relation all have the default truth value. Then by deduction, clearly I can say Tweety is a bird, and the robin is a type of animal, and Tweety is a type of animal. But when the chain get longer and longer, the confidence gets lower and lower, as we have seen. So this is understandable, I hope. Interesting part is here. How about induction? If I start from where we stopped last time, and now we know Tweety has a property of being yellow. This one is in a square bracket because it's an adjective. It's handled differently in reasoning. Then what? Then NARS can generalize it to different levels just from this one single example. You can call it one-shot learning using the terminology currently in machine learning community. But that's quite natural in logic-based system. But you can see again, the further you go, the higher you go in generalization, the lower the confidence will be. Okay? You're not that certain. You're less and less certain. But if you don't know anything else, you can still make this guess, and it's justified according to this logic. Well, of course, very often you get it wrong, especially when you have a small amount of evidence. Then what the system can do, for example, just to make a simple example, okay, for some reason the system thinks Tweety is not an animal. Here, zero means all evidence are negative against that claim. Then what? Then is the revision rule. Clearly, you see that this one and this one form a contradiction. So what you get is a compromise, not right in between. It depends on which one is stronger, right? So in this case, because this one is stronger than this, the negative one is stronger, those conclusions have a relatively low frequency. But on the other hand, both sides are already taken into consideration. You are not using the new one to completely override the previous one in this example. Okay. But that's not all, because this one is a derived conclusion, right? So that you also need to blame some of the premise which derive this conclusion, so that you will see if we follow the rules step by step, which we will not. You will see eventually everything get modified a little bit to different level. Okay. So in a sense, there is some similarity with back propagation in neural network, but the implementation process is of course completely different. And there are other rules. For example, you also can form a compound term by the system itself. If you tell the system some T is both P and Q, and then the system itself will create the union of PQ and intersect of PQ, and not exactly as necessary, but with shared intuition there. Okay, and then later this one and this one, the compound words will be treated just like their components. So gradually they will get their own relationship, which very often cannot be completely reduced back to their components. Okay. For example, what is a red light? Well, if you never heard about it, it's a light which is red, right? But gradually it gets its meaning. For example, we see it a lot as traffic signal. And that information cannot be completely reduced back to its components. It becomes a part of the essential meaning of red light itself. But so in this way, the system can generate new concepts and also can handle the meaning change in this process. So this is another big claim. In NARS does learning and reasoning, but it's the same process. There is no separate learning module and the reasoning module, and they cooperate together. There's no such thing. Okay. You can see that, as we said, each time when you're using a reasoning inference rule, you're doing reasoning, of course, but at the same time, you're doing learning. If you check, say, what's the contribution it has or long-term effect it has in the memory, well, that's the learning process. Okay, the topological structure of that concept network change over time, and there are new links created, there are old links deleted. I haven't mentioned about forgetting. There is a forgetting mechanism because of the resource restriction. The weight value, that is the truth value, get changed from time to time. That, of course, that's learning. Okay, but all of them happened as a result of inference, of reasoning. And also the system can derive its goal and desires as a part of a backward reasoning process. Okay, so that, yeah, it's just the same thing. But you can still talk about the learning property and the reasoning property if you focus on, say, that where is each truth value function come from, you treat it as reasoning, as an inference tool. Also, there are different types of reasoning which can also be unified into the same framework. Again, this is a long list. Here, I only mentioned the simplest form. Of course, each of them is much more complicated than this simple formula. I just show you that this is the code that you can actually run in NARS that will carry out the corresponding cognitive function in its simplest form. And when they're combined together, you can get very, very complicated. Okay? But you can still say, oh, this is prediction because it's talking about the future. Okay, this is explanation because it's talking about the past or something like that. But they use the same set of inference rules. And also causal reasoning, and there is no separate process. So if there is a lot of inference going on and the system assumes insufficient knowledge and resource, how about combinatorial explosion, scaling up issues? Of course, that's a traditional problem in AI, especially in symbolic AI. The basic idea, again, here is not try to get perfect solution. You just do whatever you can do as your knowledge and resource allow you to do. That's the basic philosophy. Or you can say that's also an excuse. Okay, and NARS never try to optimize a single solution. Instead, it try to optimize its overall resource allocation or attention allocation among the tasks. So everything is prioritized, and there are a lot of inference process going on in parallel, like a time sharing in operating system, where the idea come from. But different from it is the tasks and the beliefs are not handled with a sequel or with same priority. Okay, you can say it's a priority queue, but it's a priority queue where the choice is probabilistic. So everything have a chance. If you have higher probability, you have a higher chance. And also, your priority is reevaluated from time to time. So a change is highly context sensitive. Okay, if you ask the system the same question at a different moment, you may get different answer. It's just because what the system is currently thinking about provide the environment or context in which your problem is processed. Okay, it may or may not be different, the result. It depends. So it's highly non-deterministic in a sense, but it does not use random number to generate that non-deterministic feature. It's just because the environment changed and in a non-repeatable way. Okay. So also it explains a large number of psychological phenomena. Okay. Just because you don't follow a predetermined algorithm for a given problem. Okay. If you ask the system a question, basically where the answer come from, it depends on several things. Depend on what the system know about this problem, of course. Also, it depends on the priority distribution, which will decide what the system will recall in the near future when thinking about this. Okay? You cannot think about everything you know about a given problem simply because you don't have the time. Okay? So which clue or which possibility is considered first, which one second, actually it will make a big difference. Okay? And not deterministic manner, which will explain a lot of things that we observe in human mind, especially its uncertainty, unpredictability. It can be also explained in this way. Another thing is about originality and creativity. Some people still say that AI can never be truly intelligent because it can only carry out the task the user gave it. That's already not true in NARS anymore. As I said, in NARS derive its goals in a mechanism which is similar to subcoding in traditional AI, but not the same. The key difference is, say that you want to do A, and then you believe that if you do, you achieve the B, then that will lead to A. Then you are going to do B. But the problem is your belief between about the relationship between the two can be wrong, and also your knowledge is incomplete, and also your resource allocation. Actually, later, B will be treated as a goal by itself. Okay, its relationship with A may gradually get lost. Okay, if the chain becomes longer and longer, what you get is in psychology called functional autonomy. That is, your means, your means will become your ends, or your method will become your purpose. Okay, to a degree, and which is both good and bad. Okay, but for AI system, with insufficient knowledge and resource, my belief is inevitable. You like it or not. Okay, it will happen, and it can actually explain a lot of things, especially the things we do that does not have direct utility to talk about. Why you want to do that? Okay, we can explain it using this mechanism. We have multiple channels. We have already mentioned that. Okay, so that it can be used to explain a lot of things. Eventually, you'll see the system's internal experience will be handled similarly to its external experience, which will lead to topics like consciousness, free will, and so on. Okay, today we don't have the time for that, but that is addressed by this model. And it will communicate with outside world, so it will learn natural language, just like a human child learn a language. And we don't have the time for detail. And people may say, oh, you say everything is to a degree. How about 1 + 1 = 2? Of course, that's absolutely true. Okay, I'm not challenging that. But that is true in a certain context. Okay, that's true in the context of number theory or the symbols interpreted according to number theory. So NARS as a whole is not axiomatic, but it can have axiomatic subsystems. Like, for example, you can teach it set theory, you can teach it probability theory, you can teach it all kinds of math, just like how you teach a child. It just is not built into the system. Okay? It needs to be learned. And in the learning process, it will make all kinds of mistakes, just like us. But it can be done, okay, to a certain degree, of course. So, yeah, I'm almost done. So what's the conclusion? Again, I made a lot of claims today, but the point of today's talk is not to talk about any of them, is to show that all those different functions which are traditionally handled separately, both in cognitive science and in AI, can be put into the same framework. Okay? I'm not claiming NARS is done, of course, it's far from it, but we have gone very far. We have the system fully formalized, mostly implemented. We have open source project, which everyone can try, and we begin to have commercial application. Okay? But of course, there's still many open problems to be solved. But I just want to show this possibility and maybe get some people, to be interested in this direction, so we can further discuss the details. So finally, why this is good? Of course, I still believe, AI or whatever you call it should be developed eventually as other discipline of science. This is basic principles and fundamentals and mechanisms, and everything else derived on base of that, and we can still add additional small parts of there, here or there, but there should be something in common at the basis of the whole system. So for the details, interested people can check out my book, my publications, and I have about 100 papers at my website. And also NARS now is an open source project. Okay, you can check out the source code to see where we are. That's all. Thank you for listening. I hope I'll finish on time.
Thank you. Did anyone have any questions?
I would like to ask one problem which I can be biased because I'm a mathematician, is that when we look at probability theory, when we are in some situations that we see only few cases, we refrain from making a decision, because from probability theory, very often we cannot make conclusions. Here I can see that confidence function is rising very fast. We have 1, 2, 3, 4, and so on, is approaching 1, starting very fast and then slowing down. And could you please comment on this what is this change of confidence with the number of observed cases?
Thank you for the question. First, I completely agree that this cannot be done within probability theory. That is why I don't call any of my measurements probability, because it cannot be interpreted in this way. But it can be justified because my measurement is kind of like a degree of belief. That is how much the system will believe it. A stronger belief doesn't necessarily mean it's more correct. It just means that it's more strongly supported by the system's own experience, which can be biased. As the question you ask about the confidence function, you see that I didn't go into that detail. This one actually can be extended or can be replaced by any positive integer. So this is actually a system parameter, which will map the amount of evidence into a confidence measurement between 0 and 1. And we do have that application where the knowledge actually accumulated very, very fast. In that situation, actually, the basic logic remains the same. That is, no matter how big it is, if you have more evidence of the opposite direction, you can still modify it. Even if the confidence level is 0.999, it's still modifiable. But it looks bad, I agree with you. In that situation, we just use a larger constant here instead of 1. We can say 1,000, right? I will just compare each piece of new evidence, each evidence with 1,000, which with a larger unit of evidence, which will change this curve, so they will not, map almost all belief into a high confidence zone, which looks bad, even though this constant does not change any of the inference rules.
What do you think about, for instance, replacing it by learning curve, which is slowly increasing, growing fast, and then slowing down?
Yeah, a sense, yes, but it's a system parameter. It's kind of like, in some countries, currency, right? You just change the currency, say that now every $1 equal to 1,000. Okay, we can do that, and if you do it consistently, everyone become rich. Everything still works, but it just sounds different.
Okay,
it's just a unit of evidence measurement.
Thank you.
There's a question someone posted to the chat. They say, according to this unified model, is it possible to perceive other people's mental states, desires, beliefs, etc.? In this sense, how to explain when we directly perceive another person's mental state without inferring deliberatively, conceptually, their hurry, sadness, happiness, excitement, etc.?
The short answer is yes, it can be done in a similar way to how we handle local axiomatic reasoning, like in math. We kind of like build a certain context for other people's mind, simulated within it. But I don't have the time for detail. I don't want to use pause time. I will stop here. Interested people, we can communicate after the meeting.
Thank you. I really appreciate your presentation. You're one of my favorite cognitive architectures.